Okay, so what I'm going to be presenting today is a collaboration with Keutzer of Samsung. Keutzer is a integrated circuit designer who at Samsung, he and his research group, had observed our work on SqueezeNet and began to look at the potential for building accelerators that were particularly tuned to small nets to run on small processors for embedded applications ranging from autonomous vehicles to mobile phones and so forth. So at the core of this work is really Keutzer's work and my other colleagues at Berkeley. Oops. Okay, so I don't think we have to spend a lot of time on motivation. We're all here based on the motivation. But I do think my particular angle was I'm just really see the dream of ubiquitous computing, ubiquitous intelligence being realized, the potential for it to be realized for the first time. And the very particular medium for doing that are small, energy efficient deep neural nets. It's really true. And these neural nets offer the best solutions for many of the types of problems that we would like to do to bring intelligence into our automobiles, into our factory floor, into our office, even into our kitchen. And it's probably going to bring intelligence in places that we don't want intelligence, but that, as we're seeing in the broad work on surveillance around the world. So as we do that, I like to poke fun at my friends at this conference, the core computer vision types who often don't report runtimes. Power is something they get in their electricity bill, that's about as much as they know about power and so forth. And they live up here in 223 watt devices and never, or stronger, like a DGX-1, and never really think twice about it. But I think it's worth pointing out that if we want to bring that intelligence in all these different places, we've got to begin to play along this axis. And so this is all pretty anatomically correct and priced out with hours of graduate student labor of looking at different devices from a laptop down to a pedometer or iWatch Series 3 and so forth. At the front is the power dissipation, the peak power dissipation on those. That's important because the packaging and human factors cost. You don't want your cell phone to heat up too much, partially because of the cost of power dissipation in that, also because it's just uncomfortable for you to hold something up against your ear that's that warm. The second figure of these hours here, battery life, that's related to the energy, that's the integration of the power over time, and that's very related to your battery life. So we all know we get tired. I mean, I carry around chargers in my pocket just because when I'm using my GPS, my battery's likely to run out. So we went to, basically this is a long motivation that, first of all, these are the regimes that we want to operate in, which are much lower than what we have been operating in. And so we should be very concerned about power and energy. So to put that another way, so here's what you've got in the trunk of these experimental urban taxis. It's a, it may in fact be a DGX-1 or something computationally equivalent, and it's literally 3 kilowatts. That's not a number I pulled out of my head. We have, I think Toyota Research Institute has come forward and said their experimental cars pack 3 kilowatts in the trunk. Even the most optimistic notions of deploying something like an urban taxi are operating in the hundreds of watts regime. Right? But we want to be able to supply this kind of computer vision technology into a simple L1 through L3 autonomous driver assistance systems for ordinary passenger car, which means that we need to get into this 10 to 30 watts regimes, although I did hear one of the CEOs of the leading edge companies for low-level autonomy vehicles talking about they're going to pack 60 watts in their accelerator. So maybe 60, but that, as he mentioned, that will require water cooling. 10 to 20 watts will definitely get you in something that you can just operate without a fan. And then finally, we would like to get down more broadly. This is very much focused on autonomous vehicles, down to these sensors and wearables, all the way down to the milliwatt regime. So the question to us as researchers is, what can we do with 10x less speed or computational power and 100x less power dissipation? Now, the good news is the problems are familiar to us. They're problems that we have worked on for a long time. We can do all that intelligence everywhere that I've been talking about, really with some familiar problems: image classification, object detection, and semantic segmentation. So the problems aren't changing, it's just the computational requirements are. And similarly, the basic solution we will employ of convolutional neural nets or something in the neural net family, this is also not changing. This is, so there's lots that is in common here, but there are some things that are changing. Okay, so what I wanted to do is look at the most aggressive of those particular applications, which is object detection. That's the most computationally demanding of the problems that I showed you. And I have to thank the MobileNets folks. MobileNet V2 paper here did a really nice job of pricing out for, obviously for purposes of comparison relative to their latest versions of MobileNet. But what they show is mean average precision across COCO. Note these relatively small images, parameters, ops per image, and then I further price this out if we really want to. Almost everything we're thinking about employs a video camera, and 30 frames per second is a pretty conservative. Most of them go to 60 frames per second today. So looking at this, we can see, you know, this is particularly with these with more energy and efficient nets, more power, energy, and fast nets. It's not looking that unreasonable, right? Even on contemporary platforms. But that's today for object detection, and this is COCO up here. There is ImageNet, where a lot of our conference lives. Here's COCO. Here's just a good old 1080p camera, 12 times bigger than COCO. And if we want to go to Ultra HD, which is when I talk to, say, tier ones and so forth in automotive, that's where they want to be shortly, then we've got to go 48x bigger. Okay, that's the injury. Then the insult is these are super linear algorithms, right? So this is, even though the computation doesn't look too bad just a minute ago, if we really want to go to the resolutions that we'd like, we're going to have to go to a lot more computational power. So do we need accelerators? So here's some results on 835, 845, you know, very reasonable, very good performance processor for, say, a mobile phone and so forth. Gets you up to 11 to 16 gigaflops on matrix multiplication and operates at a regime about up to 4 million operations per second per milliwatt. So that works really good. And so, yeah, if you've got Peter Vita here and you want to do style transfer, you're probably set. You don't have any other worries. You can do style transfer on a mobile phone on this processor, no problem. However, if you want to do object detection at speed on a 4K video doing 30 to 60 frames per second, probably you're going to need an accelerator. And in any case, just in terms of the potential, here are 3 2018 ISSCC papers, and what we see here are ranging from 250 to 10,000x improvement in the millions of operations that we can do in a single milliwatt, right? So you can decide whether, I think as Samsung did, like, well, this is too good an opportunity to pass up, we need to get started, or if you're trying to do something very computationally aggressive, then you absolutely need something like this. So let's take a look at the basic architecture of these. At the very core, they pretty much look the same. We have a mesh of processing elements right there at the core, and I think that the new term for this is spatial parallelism. I grew up in calling this, after H.C. Kung, systolic parallelism. We're just going to pump data through these individual elements. The processing element on many of these accelerators couldn't be any simpler. It's the kind of thing you do in an undergraduate project. You just have a accumulate unit with some multiplexers to data and access to a register file. One thing that's going to be very important is to, throughout this talk, is to understand the access to the DRAM. So this is sitting off chip. And so in the crowd that I usually hang out with, you know, this kind of intuition is in their bones. I have no idea about this audience, but just think this is a long trip. As I say, if you've got to go out there to DRAM to get data, you're making a long trip. Okay. All right. So that's the core or basic accelerator architecture. Now I've given trials of this talk and seen complete confusion, gotten a lot of questions, and oh, I see. We really need to talk about different assumptions around accelerators. For most people, the only neural net accelerator they know is the TPU, and that's originally for inference, and now training and inference in the cloud. That runs on tens of thousands of processing elements, and the systolic parallelism I'm show you. It's, goes in the tens of watts regime. Your batch sizes are as big as you can get accuracy around, say in training, so it could be tens to hundreds. You have, what'll be important to see later is you have very high or perhaps even complete interconnectivity among the processing elements, and you're operating in a floating point regime, okay? So when Keutzer came, he had a very different objective. He's, looking at a single IP block to embed with other blocks on, say, a processor for a mobile phone. Okay, so we're talking 8 to 16 PEs. We're in single-digit millimeters squared. We've got milliwatts, not watts, to work with. Very important in terms of the operation of the algorithms, we're talking about a batch size of 1. What does that mean? We're going to process one image at a time, whether it's style transfer or whether we're just trying to process images from a camera in an autonomous vehicle as fast as possible. We're going to be processing them one at a time. We're not going to be able to batch them up. Okay? We're going to be hampered by local mesh connectivity. That means we can only kind of bring things into the edge of this accelerator, and then processors have to pass them to their neighbors. That's a lot different from we can pipe them in to any processor or go from any processor that we want. So kind of these are two very different extremes, and if you have the picture of this in your head, as I spend the rest of the talk talking about the one on the far right, it's going to be very confusing. So remember, we're talking about modest numbers of processors here. Now, I do want to note that there is something in between, and that's basically when you are doing an embedded processor. So, that's in the 1 to tens of watts regime. Sorry, that should be ones of tens of watts regime, and that's like this accelerator for autonomous vehicle that I heard kind of softly announced this week. So there you've got you're back in the thousands of PE regime. So that's yet another, has a little bit different characteristics, and you're probably going to do some sort of mixed connectivity among your processing elements. Okay, so you wake up and you go, well, I'm sold. I actually want to get in the business of designing one of these accelerators. Well, let me at it. What do I do? Well, what the circuit design groups around the world are doing is one quick way to get an accelerator is to reduce the bit precision. You can get factors of 8 to 32 immediately by just reducing the precision. Don't see in these papers so much attention and accuracy. Again, I'm talking about the circuits here. Another is to, people have heard about AlexNet. In defense, AlexNet has been very widely benchmarked, so there's a natural motivation to look at AlexNet. But I think if you use that kind of what is now kind of big bloated net as your only evaluator for your neural net, then you're in guiding, again, this is kind of workload driven design, guiding your design, you're going to be guided the wrong direction. And then the third thing you'll see pervasively is evaluation on MNIST or CFAR, and I think this crowd certainly knows, as researchers, computer vision algorithms, we may get some early intuitions from working on that in terms of really guiding either neural net design or an accelerator. This is the wrong way to go. So these are real papers across the top conferences, and these are real chips. And having spent a lot of time in the chip design world, I have huge reverence for anybody who manages to tape out, probe, and test a chip and show any kind of results at all. So I don't mean to trash this work in any way. I have tremendous respect. These are all, there are a lot of tired people behind every one of these papers. But in terms of presenting this as, oh, this is the way we should do neural net accelerator design, I think I can't give this a very happy face. This is not the way to go. So what's the alternative? So the alternative is co-design. I think particularly if we're doing a specialized accelerator, we need to understand our application very deeply. We should be kind of moving as a group. You know, your design team should exist of people who understand the application deeply, people who understand neural net architecture and accelerators deeply, and people who understand not just, you know, AlexNet or even MobileNet for that matter, but the principles of deep neural net design. With all three of those working together, I think we can have much better designs. So starting with the application, Mohammed, I think, already kind of set this up. If you want to do, you know, if Peter decides to do a startup and do a dog identifier application for the iPhone, and I think he could do a dynamite job, then it's really pretty important to keep all these dogs straight. On the other hand, if we're doing an object detector in an autonomous vehicle, we don't currently distinguish between a dash hound and a greyhound, right? So there's just, these are all dogs. And so obviously the accuracy that you need in distinguishing these dogs is very different. So for those of you who saw my talk at the workshop on autonomous driving, you see that I really believe, and I liked Mohammed's segment there, it's the first experimental work that I'd seen in like, okay, let's start playing with our notion of accuracy, and how does that change our whole design? That's exactly what you want to do when you want to do a neural net accelerator, or even a novel neural net targeted for a particular application. Okay, so all that said, is that what I'm going to show today? No, because I'm trying to simplify and be able to compare things. So simply to facilitate comparison, I'm not going to talk about MNIST or CFAR, thankfully. I'm going to talk about ImageNet, but we will be talking about just good old-fashioned classification on ImageNet. Okay, so focusing on that neural net accelerator design, just presuming classification on ImageNet, that's what we've been told to do. That's what we're building in some sense an accelerator for. Let's look at that. Okay, what is it that we're accelerating? Well, we're talking about computer vision, so we're talking about convolutional neural nets. If we're talking about convolutional neural nets, we're talking about convolution. So I don't think I need to spend a lot of time on this. This is just a typical convolution operation here, and creating the output from among these different, let's say 512 filters. Now, when I look at this, I mean, sometimes I've worked in so many different fields, I go, you know, what is my core competence? You know, and I think I'm really a computational scientist. That's where I live. So when I look at this, I go, this is my dream come true of computation. This is the kind of computation, you know, when I was a teenager, I dreamed that someday I would be able to be employed to compute this. And why is that? Well, you know, I've developed some terminology around parallel computation. Structure-wise, it's pipe and filtered. Simplest structure that we have, easiest to predict, just simple forward flow. From a software standpoint, I can do coarse-grained pipelining, I can do operator chaining, I can do code fusion. It's great, it's the greatest. The core computation, matrix multiply. Parallelization of linear algebra is the most studied of all computational patterns. There's nothing that's been more beat to death than linear algebra in general, and matrix multiplication in particular. And if we don't want to do anything too smart, we can rely on a lot of library support from BLAS, MKL, cuBLAS, and so forth. Another wonderful thing, we can statically schedule this computation. You know, I think people in this room take that for granted. That's not true. Most conference rooms in the world, most conferences, nothing can be, you can't even get good statistical prediction because the results are so data dependent. This thing runs the same schedule every time. So in a way, it's a dream come true in the sense of it's the simplest possible problem, but another way that means, boy, anything less than peak, and we've got to be pretty accountable for what happened. Okay, so I'm going to start something that's going to be a little dizzying. And to make my points, I'm going to find myself going back and forth between the computations we're doing and the basic architectural principles. So I will try to key you that, you know, for whom it's not immediately obvious, now we're talking about architecture, or now we're talking about the algorithm. So I was just talking about the algorithm. Now I'm back to the architecture. So this is all anatomically correct. This is done by someone at Samsung. what we have here are basically what I want to talk about is latency to either on-chip L1, on-chip L1, on-chip L2, or off-chip DRAM. And really, it's a one-liner for the purposes of this talk that we lose hundreds of cycles anytime we have to go off-chip. And so relative to the actual computation, even to go to L2, we're masking the cost of computation in our memory access. In other words, we can count max if we want to. It's relevant to do that, but at the end of the day, it's the memory accesses and the access patterns that are going to determine the computation. Thank you. Okay, so energy is even more related to off-chip memory access, and you see we actually get a 10,000 here when we have to go off-chip. Okay, so back to the computation. Now, if basically we're doing a matrix multiplication, and at the very core, we're taking an input times a weight, and we're producing an output. And if I had more time, I'd dialectically go through, but the key to making this run fast is tiling this computation, seeing where can we find the reuse in this computation. And I'm gonna have to speed up, looks like just a little bit. Okay, back talking to the architecture, we see two basic ways to support that reuse. One is, let's keep the weights resident and run the inputs and outputs over it. That's weight stationary. Or let's do partial sums in one place and run the weights and the inputs to that. It's really just that simple. So it's a big decision. Reuse is the most critical, so how are we going to support reuse in our hardware? Okay, so this is weight stationary. This is, to my understanding, what the TPU does, and I'm just going to do a quick animation of that. So basically, we leave the weights in one place, and then we pass the inputs over them, producing outputs at a time. Okay? And then output stationary, here we keep the partial sums, and I should point out this here, the last one I was showing was 16 PEs. Here, it gets really messy with 16. Here's just, we have 4. So we have 4 PEs, just for purposes of illustration. We're keeping the output stationary. And what we see is we keep those outputs stationary, and we compute the partial sums of the inputs and weights in those until finally we've completed the computation. Okay, so we often talk about computing convolutions as though there was a single convolutional net or something, a single convolutional layer. In fact, there's a lot of them. Here's our old familiar spatial convolution. Oops. Here's our familiar spatial convolution. Here's the increasingly popular pointwise convolution. Here's the depthwise convolution that the mobile net people get a lot of mileage out of. Channel, shuffles, and shift. Now, if we look across, okay, it's a little biased. SqueezeNet, you're familiar with. We presented ShiftNet this year. You'll hear about SqueezeNext later today. ShuffleNet and MobileNet. MobileNet V2, actually, this is V1, were presented this year at CVPR. And here are those different types of convolution, and here's the presence in those different nets. So if we're creating an accelerator that we think, you know, one or another of these families of nets might be a net that we want to run on there, then we need to, as you can see from this, I think the point is that we should be able to support fairly broadly across these different types of convolutional. Okay, so now back to architecture, talking about reuse. Our metric for what is good reuse is this thing called arithmetic intensity, and that's just for every byte that we pull from memory, how many floating point or let's just say MAC operations can we do? Okay, that's our simple metric, all right? And what we see is that these different blocks, these different convolutional types of convolutional blocks have very different behaviors. So these are we can figure this out statically. So here's the algebra at the bottom. Note that we're not distinguishing here between a register access and L1, L2, or even going off chip. We're just saying in general, how many bytes do we need to pull these? So we normalize this to a good old-fashioned spatial convolution, say a 3x3. And pointwise doesn't do quite as good. Neither does group convolution. But boy, depth-wise has a lot of problems. Its arithmetic intensity is 50 times more. So that means that we're going to have to do kind of normalized 50 times more memory accesses. And here are the particulars. So this is not outrageous. This is not made to make depth-wise convolution look bad or something else look good. This is just kind of a vanilla middle layer of your neural net. You can check out these numbers. And again, the main point is there's a factor of 50, although we think of these convolutional layers as kind of the same, or kind of, we're computing convolution, we have factors of 50 differences in their data reuse. Okay, so now back to the architectures. So we're looking at output stationary and wait stationary, and we're going, oh, actually, unfortunately, if we want to support these broad convolution types and these different layer configurations, maybe in the interest of time, I'll just point out the simple fact that, well, output stationary does pretty good when you have lots of intermediate output partial sums to compute, but when you have fewer, it doesn't do as good. Wait stationary does fine on those pointwise convolutions, which is good. We'll see that that's like 95% of some modern nets, but is very poor in depth-wise, which is another popular type. So that's not so good. So to look at the particulars of distribution, so here's another another family of different nets that we looked at, and basically the percentage of the total max that are consumed in the different layers types. Now, I'm pointing out here, this is where wait stationary does really bad. This is where output stationary does really good. This is where output stationary does really good. So what we see is quite a mix of different types. So the conclusion, again, if I was in a classroom, I'd do this dialectically and really enjoy the different answers. In this interest of time in this talk, I'll just get straight to the punchline. Well, I don't know. Why couldn't we support both data flows? So that's exactly what we did in the Squeezelerator. Basically, it's a hybrid wait stationary and output stationary data flow. I'll be talking about it next week at the Design Automation Conference, but kind of forecasting it for you today. So I think with enough pomp and circumstance, I think I could convince you that this was a brilliant observation. Maybe right now you're just thinking, oh, well, that was pretty obvious. But those are not inconsistent. Brilliant can also be obvious. And if I did it myself, I wouldn't be talking that, but Keutzer is the real person who had that light bulb in his head. Okay, so how does that do? So here's output stationary architectures, here's wait stationary, here's the Squeezelerator, and you noticed Keyser's original motivation is let's see how we can do on SqueezeNet family, and he saw this big spike here. So, sorry, this is total execution time, and this is the amount relative speedup of one architecture over another. So basically we're looking at how well does the gray bar do against the other two. And in making this run well on the SqueezeNet 1.0, what you see is he really did a heck of a job on MobileNet, which is, for some of you who've tried to make it run really fast, a very finicky net to try to get performance on. So 6x in our world, that's a really good day. Okay, so now I want to jump, with all this talk about reuse, I want to jump all the way back to applications and talk about application characteristics. So Vivian Say is another one of the pioneers of our area. She's raised awareness around architectural concerns for supporting neural nets and importance of power and energy and so forth. And she drives me crazy when she puts this up. This is normalized energy consumption, so going this way is worse. And she stands up and says that SqueezeNet consumes more power or more energy than AlexNet. And I have kind of a twitch every time I see this. So again, I do this dialectically. What's wrong with this diagram? It took my grad student, Bi-Chen Wu, a lot of time to figure it out. But although often unstated in 6 or 7 papers that she publishes, she's presuming a batch size of 44 to 46, which basically says that with AlexNet, all those big hulking weight parameters doesn't matter so much because you get to reuse them over and over and over on her architecture. So there's not much penalty. On the other hand, if you look at our results, so here higher is worse. and you look at a batch size of 1, again, we're processing 1 image at a time in times vehicle, we're doing 1 style transfer at a time, we see SqueezeNet, I think, just where it belongs, the most energy efficient among all these nets. Okay, so in terms of co-design, in my presentation next week at Design Automation Conference, I'll be then talking about, okay, now that we've got a lot of insight from the architecture side, let's go back and look at the net. And what we did was, driven by Amir Gulami, we went from SqueezeNet to SqueezeNext. Unfortunately, he's got a poster here, and you'll be hearing a brief presentation on that in just a moment. So, to summarize, I think we're going to need neural net accelerators to meet the constraints of the embedded vision applications. And you can sit there and go, well, is it a good to have or a must have? That probably depends on the application, but why not, right? If you're going to do that, this kind of old-fashioned, well, let's get some workloads together. Oh, somebody brought up AlexNet. Oh, somebody has CVPR somewhere. Okay, let's see how it does. That's not the way to do it. What you want to do is a detailed, layer-by-layer analysis of contemporary DNNs. And as you'll see in that, the key to efficient DNN computation is data reuse. And in different convolutional neural net layers, as I showed you, have factors of 50 differences in their patterns of reuse. So, and different accelerator architectures then support different types of reuse, outputs versus weight, better or worse. So to try to kind of take the synergies of all those insights, what we've done is we've developed a neural net accelerator designed the Squeezelerator, which is supposed 2 of the most popular data flows. We didn't have time to talk about some of the others we considered, and matches the data reuse in the accelerator to the characteristics of the layer. And in that way, we were able to get a 6x speed up over other accelerator architectures. And again, we're presuming you've already got the 1,000 or so by just going to an accelerator. And now among different accelerator architectures, we're getting another 6. Okay, thank you.
I think it's a great talk and very interesting work. I hope my question makes sense. So I see that you're looking...
Would you mind introducing yourself?
I'm Eric Castillo. I work at NVIDIA.
Okay, thanks.
Autonomous. And very interested in compact DNNs.
Me too.
Believe it or not, yeah. So I see you're working on these core elements, the convolutional pieces. A lot of the innovations I see at a conference like this are about the interconnections of those things. And some of those interconnections imply, like for example, take a skip connection, which goes from an early stage to a later stage directly, but that implies a long latency, which implies memory.
Yep.
So are you looking at those kind of issues?
Yeah, we are. So I have some analysis of DenseNet. So it's a great question, and the kind of question that comes when you stare at this for a long time. So the way reading it back to you, boy, these nets which do aggregation and skip layers and so forth, seems to really help accuracy. Well, how's that do for computation? Not anything very good on something you're going to do an accelerator. Again, for data reuse, this is something of a nightmare. So in the original talk, I had data on those. I kind of made the executive decision that for the purpose of this audience and talking about what are likely to be popular neural nets that you'll see, I don't see those aggregate layer architectures playing a role. Now, maybe in 6 months somebody will show how to do that. I don't know exactly how to do that today.
Thank you.
Sure.
Thanks for a great talk. My name is Philip Leong from the University of Sydney.
Great.
And I was just wondering, so this is kind of, if you want to make a chip that's, to accelerate things, but have you thought about more fundamental operations or things that you could supplement a CPU with in order to kind of support this sort of thing? Because, I was thinking that the type of network that you're describing now would be different to the one you would have done 3 years ago, for example.
Right. Yeah, so again, reading that back to you is like, okay, I mean, I heard a couple things there. Number one, what about the diversity of original neural net design? And are you heading in the direction of, the second question is kind of like, are you heading in the direction of, well, can I just add a few more CPU instructions and get more malware out of this? Is that something like that?
That's the
Yeah,
thing.
well, these, again, when I talk to Keutzer about, neural net accelerators, he just sees a vector unit, right? So this mesh of PEs, we're calling it an accelerator, but it's been studying architecture for 30 years. So if you were CEO of ARM or something, I know CEO of ARM, anyway, and Brian Seegers, Dennis Seegers, I think. So, if he came up and said, what could I do to turn our ARM into a neural net accelerator? So just put a vector unit on the side. So that's not a big deal. But I'm glad you asked about these novel architecture types. My student Bi-Chen Wu gave a talk at CVPR this year, a spotlight presentation on Shift. Shift is a really interesting zero-flop operator, which basically just moves pointers in memory. So that's exactly the kind of thing, we're trying to win the battles that we're fighting, but we're also trying to find ways to outflank the computational enemy and obviate some of those computations as well. And that's what's fun about looking at applications, neural net design, and architecture altogether.
Okay, thank you.
Hello, my name is Edwin Park from Qualcomm. If you were designing your own chip and you had SRAM capabilities, and you're willing to put either the parameters there or obviate some of the burst mode problem and DRAM accesses for, let's say, the pointwise 1x1 convolution, how would all those curves look different?
Yeah, so what I heard you say is if I could design my own chip and I had control over the memory size.
And specifically put SRAM instead of taking it all the way to DRAM.
Yeah. So, let me leap over to another. So again, it'd be very application driven. We have a paper into NIPS this year. Who knows if it'll go in? But basically, if you're doing LSTM acceleration, then getting the LSTM model into on chip, there's a lot that we can do. So if you told me that, well, and we really want to be able to, at Qualcomm, we want to be able to recognize speech better than anybody else, I say, yeah, let's see if we can't do a lot of SRAM, fairly modest computational structure, and I'll bet we can do really well with speech recognition. Now, if we're doing convolutional neural nets, we currently still have to crank through a lot of matrix multiplication, and therefore the trade-offs, again, it depends on precisely how big image you want to process, what your latencies and so forth. But SRAM is, so thank you for bringing up SRAM. It is a first-class citizen. The devil's in the details in terms of how big it should be.
Okay, thanks.
Sure.